that there is no square root. So then what we discussed with you the stress energy tensor. We are now thinking about string worldsheet action as 1+1 dimensional quantum field theory. This is an example of 1+1 dimensional quantum field theory. Actually, we also have a metric here, so we can think of this as a 1+1 dimensional theory of scalar fields coupled to a gravity. And so what we ended up talking about the stress energy tensor, and I reminded you that the way how the stress energy tensor is computed in quantum field theories. What we have to do, we have to take an action, and we have to vary it with respect to the background metric. And that would give us the stress energy tensor. So this is a definition in string theory, and it differs by some factor from quantum field theory. So also, when we discussed this action, so this action has a bunch of very nice properties. So in particular, it has two-dimensional diffeomorphism invariance. And so in particular, as a consequence of this two-dimensional diffeomorphism invariance, the stress energy tensor must be covariantly conserved. And so the derivation, I was pointed out late after the lecture that I was a little bit cavalier in my derivation. And so when I was doing this derivation, pretty much following Wald, what I missed is that in general, there would be contribution due to the variation of the matter fields. And the way to get rid of them and actually have this conservation of the stress energy tensor, I must put matter fields on shell. So this is true, provided that X mu satisfies equation of motion. So this is only condition on shell. So then the second invariance of this action is a wild invariance, right? So this is an invariance when we take a metric and rescale it, gamma AB. So our Polyakov action is invariant, and as a result of this, so we can derive the following identity, that the trace of the stress energy tensor must vanish. And actually, in order, this is an identity. In order to do that, I don't have to use equation of motion. And the reason for that is that under the Wild transformation, matter fields does not transform, and coordinates don't transform either. So that's where we finished last time. And so now, what we will do, we'll just compute the stress energy tensor in this theory. And so let's just do it. So I have TAB, right? So equals to minus 4 pi root minus gamma. And then I have minus 4 pi alpha prime. So now I have to vary the action, delta over delta gamma AB. Sorry, with the lower indices, right? Absolutely correct. So let me, I'm not gonna, well, there will be an integral here. So I have to, what I'm doing right now, I'm varying this piece first. So this gives me 1/2 minus gamma to the minus 1/2. That's from variation of the square root. And then I have gamma AB delta gamma AB. And I have nothing, I'm not touching this combination, right? So I'm just going to use a shorthand notation. So I'm just going to define this to be del x squared. So that's one piece. And so the second piece will come, so that's when I varied the square root of the worldsheet metric. Now I have to vary this. But I want to write down the variation with the lower indices, right? So, and remember, the delta gamma AB, that would be a natural variation coming here. But remember, one of the formulas that we discussed, that's the same as delta minus gamma CD, gamma CA, gamma DB. So if I try to lower the indices of the variations, there will be an additional minus sign. So what that tells me is that I will have a minus sign here, and then I have minus root of gamma. And now those components of the metric I have to use to raise indices on del x. So I'll end up having del A x mu, del B x mu, okay? So, times delta gamma AB. Okay, so very good. So any questions? Sorry?
You still have gamma.
Well, that's in here. That's what I meant, del x squared.
But you still have, you just variation. You still have
right?
Minus gamma.
Oh yeah, sorry. There is a determinant. Yes, you're absolutely right. There is a determinant. Right. So variation of gamma is gamma AB delta gamma AB. Thank you. Yes. Okay. So very good. So now, right. So this gives me a square root. So minus all the minus signs will cancel there, and I can write it down. So usually minus. So here altogether there is a plus side. So if I take conventionally, I'm writing it in the conventional form. I want this term with a plus sign. So it will be minus del A x mu, del B x mu, and then minus 1/2 gamma AB, del C x mu, del C x mu. So that's the stress energy tensor of our quantum field theory. Okay. Now, so what I want to, so first of all, you can see that, you can see those two facts that I said here. So in order to show that the stress energy tensor is covariantly conserved, I indeed need to use equation of motion. However, the tracelessness of the stress energy tensor is automatic, right? So TAA, so this combination will give me minus del x squared, and this guy gives me minus 1/2 gamma AB del x squared, and that's going to be equal to 0. So that's again just a reflection of the fact that when I do a Weyl transformation, it doesn't affect neither the coordinates nor the matter fields. Right, guys? So we're done with this. So now let's talk about equations of motion, right? So dynamical fields. Dynamical fields, in our case, are the background metric, gamma AB, and then there are scalar fields on the wall sheet, x mu. So delta S over delta gamma AB, so must vanish, right? However, it's clear, if you recall the definition of the stress energy tensor, up to a factor, that's exactly the stress energy tensor. So one of the equations of motion is vanishing of the stress energy tensor. Now let's derive the second set of equations of motion when we vary the action. With respect to scalar field x mu. So that's equal -1 4 pi alpha prime and integral d tau d sigma and minus gamma, gamma AB, x mu, nabla B, x mu delta. And actually there is additional factor of 2 here, right? Because I can vary either of the axis that I have there. And so now I will do a sloppy thing first, and then we'll go back and look a little bit careful. So I'm going to integrate by parts, and so now this covariant derivative will act on this combination here. So I have minus, so minus will turn into plus del tau, del sigma. So I have nabla B square root of minus gamma, gamma AB, nabla A, x mu, delta x mu. Okay, so plus boundary terms that we'll talk in a little bit. So, so this variation must vanish. So we're assuming that we have the right boundary condition for now. We don't care about them. And so that gives us the equation of motion, nabla B acted on square root minus gamma, gamma AB, nabla A of x mu must vanish. And so if you remember wall, then the combination here is precisely the del inversion. More precisely, it's root minus gamma times del inversion. And so our fields satisfy massless Klein-Gordon equation. Okay, so in 2 dimensions. And that's an equation on a curved background. Okay, so now let's go back and look more carefully at the boundary condition, and we'll try to figure out what kind of boundary conditions we can impose if we want to preserve the symmetries of the Polякov action. So one of the symmetries of the Polякov action, which I did not mention yet, was the Poincare invariance in the ambient space. And so first, we would like to figure out what are the possible boundary conditions. Possible boundary conditions that preserve Poincare invariance in I forgot what notations I use in D dimensions, okay, in these space-time dimensions. Okay, and so it's actually very easy to see. So there is this boundary term that I did not write down. So that's the term of the type, right? So I have to integrate by parts, and so there will be in general the boundary term alpha prime. So there is an integral from minus infinity to plus infinity d tau. So I have root of minus gamma, and then I have gamma so again, so I'm assuming here that we have only space-like boundary. So the time goes from minus infinity to plus infinity. So the boundary term can come only when we integrate with respect to sigma direction. And so what this tells me that it must be sigma times A, right? And then I have del A x mu, and then I have delta x mu. So that's a boundary term that would come there. And so we need to evaluate it when sigma equals to 0, as sigma equals to L. So we're assuming that our string stretches the length over the length L. Okay, so before I continue, any question? Any question?
So what is
Gamma sigma A.
Gamma sigma A. So this it's just this piece, right? So if you look down here, all I'm saying is that the boundary comes only from integration with respect to sigma. So the only thing I need to care carefully when I do integration by part, when I have del sigma here, which tells me that the index B equals to sigma. So I still have a summation over the A index, and so that's what I wrote there. Okay, so in order to have the equation of motion that we derived there, massless-Klein-Gordon equation, so what we need the vanishing, and to have a well-defined variational principle, we need the vanishing of this boundary term. And so you can see that there are two ways how this boundary term can vanish. So the way to make it vanish is to enforce this condition. That's one possibility. So we can declare that del sigma of x mu of tau 0 equals to 0. Del sigma of x mu of tau L equals to 0. So that's one way of imposing boundary condition. And so this is known as Neumann boundary condition. Okay. And so another way, and notice that this boundary condition is actually Poincare invariant, right? So because once I do Poincare transformation on x mu, I will still get zeros on the right-hand side. And so those conditions preserve external Poincare invariance. So that's one way to do boundary condition. And so notice that in this case, this type of boundary condition implies that our string has ends. So we have Neumann boundary condition for an open string. By that, I simply mean that the string has endpoints. Okay. Another type, another way of imposing this condition is to require that our fields are periodic. So in other words, x mu tau sigma we can identify with x mu tau sigma plus L. And so in this case, obviously, there will be a cancellation of this boundary term. Of course, immediately you can see that once I impose the periodic boundary condition, exactly the same condition I must impose on the variation of this field. So note that delta x mu must be periodic as well. Okay. And so what this tells us that in fact we're dealing with the closed string. So we identified, as we go around in this sigma coordinate, all the fields become identical. And so it's natural to think that we identify sigma plus sigma of L. And in other words, we're dealing with closed strings. So the second type of boundary conditions, which are consistent with Poincare invariance and gives a well-defined variational principle of Polyakov action, are these closed strings. So finally, I'm sure that some of you have heard that, well, there is a Dirichlet boundary condition. So let me talk a little bit about it. And we'll return back to them later in the course. So Dirichlet boundary condition. Just one second. So let me explain what that is, and then I'll answer the question. So what's the Dirichlet boundary condition? Delta x mu of tau 0 is exactly the same as mu of tau and L, the variation equals to 0. So the ends of our string are tied up to certain hypersurfaces. So in other words, what that tells us that we keep x mu of tau 0 equals to a constant, and tau L equals to a constant. Questions?
Periodic boundary condition implies that variation in both ends are equal, but how you're taking
This delta?
Yeah, from delta to how you arrive on periodic boundary condition. I mean,
no, I'm just saying that it's consistent.
Periodic boundary condition is there, then this variation will vanish.
Right, so I'm just saying that, so we are trying to figure out what kind of conditions we impose on our fields, right, in such a way that this boundary term would vanish. And once this boundary term will vanish, then our equation of motion will be what we derive on that level. And so what we are concluding, we guessed, if you wish, two types of boundary condition in which this term is vanished. The first one is a trivial one. All I'm saying is that this term vanishes. But the second way of doing this is to say that all the fields are periodic. So if all the fields are periodic, actually what I didn't mention is that this guy, including the background, the Walsh method, it's also periodic. So everything is everything returns back to its own values. And the important point here is that once our fields are periodic, then we must impose the same condition on the variation of the field. So this delta x mu is periodic as well. So in other words, all this combination is periodic with a period of L. And so here you have this combination subtracted at 0 and L. That's why it's vanished. So those are two types of boundary conditions. So now what I'm going here is to point out that there is another trivial way, but it has been overlooked for quite a long time. And you guys will tell me why. Even though it's a trivial way how you can get everything that we discussed before and sort of make this boundary term vanish, all we have to do is to require that delta x mu will vanish at sigma equals 0 and L, and that leads to the following conditions that I said. So why did it took people so long time to actually explore this? And can anybody tell me? And this actually is something that had a very deep implication. So that's discoveries that led to D-branes. And you know how important D-branes are in string theory in various aspects, understanding theory, non-petrolative. So in other words, why did it take Joe Polchinski to figure it out? Right. Any suggestions?
Energy conversion or momentum conversion.
We'll talk about quantization of string and energy and momentum much later. You should be able to answer this question, what you know so far. So any ideas? Yes.
You're basically holding the ends of the string fixed in space.
Yes.
That's just like the rest of the string fairly proper.
Yes. And what's wrong with that?
Yeah.
Eventually, we know it's not wrong, and it would lead to discovery of additional, objects in string theory. But why it is wrong? Well, given everything that I talked so far. The crucial word, and I kind of emphasized it, is that we were looking for the boundary conditions which are Poincare invariant, right? So which means that our boundary conditions are invariant as we make translations and Lorentz transformation in the external space. So now what's happening here, once I pin my string to a certain hypersurface, to a certain point in space, that condition is not invariant under Lorentz transformation. It's not invariant under translations. So those hypersurfaces, the D-break, they break the Poincare invariance of a space-time in which our string propagates. And that's why people discarded these boundary conditions to begin with. The idea was we're going to try to impose very rigidly this Poincare invariance. And so if you do that, then those are inconsistent boundary conditions with Poincare invariance. So what it's done is it breaks Poincare invariance. Okay, so is that clear? So we'll go back to it, and it will be interesting to explore what are the consequences of this. Okay, so all right, guys. So So here, when I wrote these boundary conditions, I want to just write them down in slightly more covariant way on the wall sheet. And so the idea here is that, well, here I kind of make an assumption that my wall sheet is oriented in such a way that sigma, the endpoints of the sigma interval are the boundaries of the open string, but I can be more general, right? And so if I am more general, so let me go back to this boundary term, and I'm not going to make any assumption about the orientation. In other words, I will try to write down this condition, particular this one, in a more covariant way on the wall sheet, right? So this guy is not very covariant because I had to choose the sigma variable. Okay, so how do we do that? Well, so let's look back at our boundary condition. So it's -2 over 4 pi alpha prime. And then I have, so the boundary, I shouldn't put an equality sign because there is additional, well, okay, so I can put equality sign and write it down in this way. So del tau, del sigma. So that's an integral over the wall volume, over the wall sheet of our string, and then I have del d, right? So when I integrate by parts, so we'll use this term del d square root of minus gamma ab del a x mu delta x mu. Okay. So that's before what I actually wrote. So what I wrote on this blackboard, I just assumed that the boundary is only at the endpoints of the sigma interval, and then this derivative becomes del sigma. So I integrated this total derivative, and I get sigma equals L, sigma equals 0, but I want to do it in a more general case. So I'm not making any assumption here. I'm just saying that there is a two-dimensional manifold M, and so that would be the boundary term. And so here I want to remind you that that if I have, so here you can, I think I like very good. There is a very nice book by Nakahara, Geometry, Physics, and something else, I forgot. So when I was in graduate school, that was my Bible. So there you can learn a very beautiful formula which tells you that if you integrate over a manifold M, can be arbitrary dimensional, some vector field, a derivative of a vector field, so it's del A dA. So then this is the same as an integral over the boundary of this manifold. And here I have NA times BB, where NA is an outward pointing normal to the boundary. So this my manifold M, right? So this is my boundary. This is del M. And so at each point, I can construct an outward going normal. So if I use this, so this is the generalization of divergences theorems that you derived before in various aspects of your calculus. And so if I do it, I can use this theorem here. And so this becomes -1 over 2 pi alpha pi. So then I have an integral over the boundary of NB times del del d of x mu. Okay. Del x mu. And so a covariant way of writing that boundary condition is going to be in this form. Okay. So here notice that I have summation over the wall sheet indices in the right manner, and so that boundary condition is actually wall sheet covariant. So this is again Neumann boundary condition. all constrained. Okay. Okay, very good. So, so far we discussed particle string and dynamical degrees of freedom, which is on the black with is going up there, as a metric, and the scalar fields x mu. So now, what we would like to do, we would like to try to generalize. And we want to ask the question, in some sense, how unique is particle action. So in other words, we make the following assumption and try to see what else can be in there. So we're going to assume the same symmetries. And by same symmetries, I mean the three symmetries our Poincare invariants in d dimensions, Diffie invariance in 1 + 1 dimension. And the third condition is the Weil invariance, which we will see later is a very powerful. Well, first of all, you will see that that's going to be the first aspect how powerful it is, because it will select us a certain class of possible generalization. So we impose Weil invariance. So that's the first condition. Second condition, we want to deal with action so that we know how to deal. In other words, we want a two-derivative action. So there are issues if we have high derivative actions. So we need two-derivative. We want two-derivative action. And second, for now, let's don't introduce any additional fields, right? So let's not introduce any additional fields. So for now, we'll assume that the set of our dynamical field is as before. So in other words, we are asking is, given the symmetries to derivative constraint, is there anything else we missed when we were writing down this 1 + 1 dimensional quantum field field? Okay, so first of all, we can, if you think, and I encourage you to think for yourself, but it's pretty much clear that since we can have only one derivative, so this piece can only enter linearly. Okay, so this can enter linearly in particle action. And so we already have one term in which is linear. So the only thing available that we can write down. So we already have this term, MIAB del x squared. So if you wish, so the only thing that we can write down, as long as we restrict to a two-derivative action, something that well, so you might try to construct something that doesn't depend on the derivatives of x mu, but if it doesn't depend on the derivatives of x mu, you will immediately run into problem with Poincare invariance, right? So you need to differentiate s so that whatever enters in this action is invariant with respect to translation. So what I want to say is that this something can depend only on gamma AB and nothing else. Okay? So are you with me? Agree with that? Okay, so if that is the case, then we have to ask ourselves. So we have just metric, and we want to construct objects which are invariant under diffeomorphism invariant. And so those objects must be differential invariance on our manifold. So must be geometric invariance. Now, we know those geometric invariants. Those are, for example, the square root of the determinant of the metric, and another possibility, various ways how we can construct curvature invariants. Now, if we restrict only to two-derivative action, and by two-derivative I also mean two-derivative with respect to the whole-sheet metric, then the only things that we can construct is the curvature invariant, the Ricci scalar. Anything other than that, upon the variation, will give higher derivative action for gamma AB. And so something that we can construct, the only piece that we can construct is going to be, must be diffeomorphism invariant. And so it could be just this term. Okay? So this is a potential new term. Okay? So let's discuss this term. So first of all, we need to see if this term is invariant under diffeomorphism invariant. Okay, so let's see. So I'm doing well. It's invariant. Sorry, it's invariant under diffeomorphism invariant. So the only thing that we need to check is a while invariance, right? So while invariant. Okay, so let's do while transformation. So gamma AB goes to e to the 2 omega gamma AB, and square root of minus g goes e to the 2 omega square root of minus gamma. And so the next thing we want to know, how does our Ricci scalar transform when we rescale a metric by a second factor? Okay. So let me give you first an intuition. Okay. So let's talk intuitively, and then I'm going to write down a formula from the wall. Of course, I could have written the formula to begin with. I want you to get a feeling also what's going on. So let's look at the sphere, right? So if I look at the sphere, and suppose I have a sphere of radius 1. So, and I'm asking, so this is a sphere in 2 dimensions, and I'm asking the question, what is the curvature of the sphere? Well, it's going to be equal to, right? 2 divided by 1. So this is a Ricci scalar of the 2 spheres. Now, what will happen if radius of the sphere becomes L? So I scale the radius of the sphere by a factor of L. So, well, you know that the Ricci scalar in this case will be 2 divided by L squared. But once I scale the size of the sphere by a factor of L, what happens is that the metric on the sphere scales by a factor of L squared. So I'm making my sphere larger, so the metric I'm using has a factor of L squared here. So what I'm trying to give you an idea is that once you do this while rescaling, the Ricci scalar will transform into Ricci scalar e to the minus 2 omega, which is exactly what's happened here for the sphere when we simply scale the radius of it, right? So if we scale the radius, the metric and the Ricci scalar transform in an opposite way. And so this would be correct. This would be correct if omega, well, del omega of A would be 0. So in other words, if our while parameter would be a constant. So that would be a correct statement. However, because in general, omega is a function of the whole-sheet coordinates, there will be additional terms that come in here. And so those additional terms, I'm just going to write it down for you. And you can look in the wall, and that's one of the appendices. I forgot, probably appendix E. So first there will be a term that's the old Ricci scalar times e to the minus 2 omega. And then if we do it in the general d dimensions, then there will be a term like this. And then there is a term d minus 2, d minus 1, nabla omega squared. Okay? So in general, the Ricci scalar under Wild transformation transforms in a non-trivial fashion. So the case of interest in our story was a Polякov action, little d equals to 2. So this term vanishes. However, we still have to deal with the first term. And so under Wild transformations, d tau d sigma squared Einstein-Hilbert term on a string wall sheet will transform d tau d sigma. And then I have here square root of minus gamma e to the 2 omega e to the minus 2 omega. So here I have r minus twice box omega. Okay? And so this is an integral over the wall sheet of our string. And so you can see that those things happily cancel. We have what we had before, but then there is an additional piece, so extra term. So this extra term is minus 2 integral d tau d sigma, and then I have square root of minus gamma box omega. Okay, so how do we deal with this term? Well, so first of all, box omega is the same as covariant derivative del A acted on the scalar omega. And so what I can do, now I can take this del A and move it past symmetric, right? So we know that one of the features of covariant derivatives is that it doesn't act on symmetric. Symmetric is covariant to constant with respect to covariant derivative. So I can write it down, this guy times nabla A, and then I have square root of minus gamma, nabla A, omega. And so you can see now that I can use Gauss theorem and rewrite this as an integral over the boundary of my space. So now here, that's a total derivative, so that becomes NA times minus gamma nabla A omega. Okay, so what you can see is that in general, imposing Wild invariance with this additional term adds additional constraint. So we want that this term vanish. And so you can see that there is an obvious situation in which this term vanishes. And so the obvious situation is closed strings. Closed strings. So this additional term vanishes for closed strings simply because the string is closed, and so there is no boundary. It doesn't have any boundary. And the reason for that is that del m equals to 0 in that case. There is no boundary, the term doesn't appear. So you can think of this along the lines we discussed before, because we have a closed string, all the fields are periodic, and you can show that once you integrate by parts, everything will cancel. Well, it's not integrating by parts, simply integrating this total derivative. So for open strings, it's a non-trivial condition, and this is one of the problems in Polchinski book. I'm not going to do it here. But for open string, it's not immediately the case, and you would need to add additional terms. But it is possible but not trivial, to generalize to open strings. And so this is an exercise in differential geometry, and the answer is given in a Polchinski book.
Alex, can I ask you a question about, could we just say that, could we pick up the term which will be while invariant? For example, we can make something from while tensor and
No, while tensor is already wait. So while tensor.
so maybe we can make something.
You need still to contract while.
Yes, yes.
Once you contract, the only thing you will get is Ricci scalar. As long
So
as
we cannot make.
no, not unless you don't want higher powers of Ricci tensor or RAB squared, right? Right, guys. So that's all we can have, right? So what at least I convinced you for the closed strings, such an additional term might exist, and so our next, and I told you that it can be included even for strings with boundary, open strings. So our next task is to ask, will it change the story, everything that we discussed so far? And so what that means that we have to ask our question, how does this term, additional term, how Einstein-Hilbert term on a roll sheet would affect our equations of motion, right? So eventually we want to solve the equation of motion, find the spectrum of fluctuation of the string. And so it's clear that this guy is not going to be affected, right? So this will get exactly the same equation of motion as before, because here we vary the scalar field and not the metric. However, there was an additional equation of motion where we varied the action with respect to the background metric, and so we can do that. And so if you do the variation, if we do the variation of the Einstein-Hilbert term, sigma, so what you will find out, so this is an integral over m, so you'll find out, again, this is just the standard stuff from the wall, gamma AB times R, and times delta gamma AB. Right, so not a surprising thing that if you vary Einstein-Hilbert term, as a result of this variation, you will get Einstein equations. And so here, this term will produce an Einstein equation in 2 dimensions. And that's going to be a correction, right? It's going to be a correction in principle to the stress energy tensor that we computed before. Now, here, the special situation is that we are in 2 dimensions, in D equals 2 dimensions, and so you can do the counting how many independent components Ricci tensor has in D dimensions, and so the answer is, so again, you can look in Nakahara book. That's where I copied this formula. So a number of independent components of Ricci tensor AB in D dimensions is 1/12 d squared minus 1. And this is true when D is less than 4. So if we substitute in this formula, D equals 2, so I have 4 times 3 divided by 12, so I get 1. So in other words, a Ricci scalar in 2 dimensions has a single independent component. And what this means is that whatever it is, it must be proportional to gamma AB, right? So I need an object that carries the same index structure as the Ricci tensor. So it must be that's a background metric gamma AB, And so here I have, in general, arbitrary coefficient lambda. And this arbitrary coefficient lambda is this single independent component of the Ricci scalar in 2 dimensions. However, we can compute what this lambda is. So what I can do, I can take a trace on both sides. And so I have Ricci scalar equals to lambda times 2. So in other words, my coefficient lambda is 1/2 times the Ricci scalar. So what we are finding is that in 2 dimensions, there is a very peculiar identity that the Ricci scalar RAB minus equals 1/2 R gamma in B only in D equals 2 dimensions. Okay? So what happens then that once we vary our quadratic action with Wolfschild-Einstein-Hilbert term, indeed we will get this contribution, but this contribution will identically vanish because of that peculiar identity. So our conclusion is that making the quadratic action while invariant and the most general possible, we still get the same equation as we discussed before, and this additional term, square root of minus g times r, does not affect our equation of motion. Okay. So another way to say it is that it's a topological term. So in fact, if you compute this integral, that's proportional to the Euler character of a surface for closed flow sheets. Okay, so in other words, use topological term. So now we have the most general Wolfschild action. I can write it down. Del tau del sigma square root of minus gamma 1/4 pi alpha prime gamma AB del AX mu del B x mu plus lambda. So again, just a conventional linearization. Lambda over 4 pi times Einstein-Hilbert term. So it doesn't lead, we showed that that's the most general while invariant action. So this additional term comes with its own constant. So additional constant. Okay, so I put constant in brackets because I advertise you that in a string series there are no parameters, there are no free constants. So what actually happens is that this constant is related. In a string series, there is a field that we will derive with you probably in either this lecture or the next one. There is a field which is a dilaton, so that's a massless field. And so this constant can be shown to be related to the expectation value of one of the excitations of the string. So it's not a free parameter, it's just an expectation value. So this term is topological. So even though it doesn't contribute to the equation of motion, but it will distinguish Wolfschieds of different topologies. So in particular, if I look at closed Wolfschieds, which look like a sphere, the Euclidean Wolfschieds, and so if I look at Wolfschieds that have a different topology, say a 1 torus, then the contribution of this term here and here will be different. And so you can think of it that this is the term that would organize the string theory perturbative expansion in terms of complexity of our Wolfschieds. So this is we'll get back to this issue when we talk about loop corrections in string theory. So that's the term that will differentiate world sheets of different topologies. Yep.
It's always oriental, and 2D, the only topology invariant is the
Yes, so we talked about orientable world sheets, but it doesn't have to be this. So you can consider world sheets which are non-orientable. And so there is a way of incorporating that. Right? So we'll get back, I promise you, we'll get back to this topic. Very good. So we talked about the polycorrection, and we saw how special it is. And again, it's special because, well, we require while invariance, and we require, you know, two derivative actions and all these conditions. But given those conditions, it is special. However, you might ask the question, are there any further generalization of the polycorrection? And the answer to that is yes. So that includes introducing extra fields on world sheet, and so in particular fermions. So this is volume 2 of the Polchinski book, and I will mention why. So all I'm saying is that it is possible to generalize it by introducing additional fields. And those additional fields actually are required. So they are precisely the type of fields that will make the string theory action supersymmetric, and the supersymmetry is necessary in order to not get garbage predictions from string theory. Otherwise, we'll be getting at least the best thing we can do is to try to do perturbative analysis. And what we will do, we will find out that there is a tachyon, and so our vacuum is unstable. We will discover that. So what we will see is that I'm not going to talk about this at all in the course, but you will see that something like that must be done. Otherwise, everything that we talk about doesn't make sense. And it doesn't mean that what you learn here is worthless, because everything, it's really much like, you know, with this Einstein-Hilbert term on the world sheet. Everything you learned before Einstein-Hilbert term was okay. Now you realize there is this Einstein-Hilbert term, but that doesn't change anything. The same thing kind of here. So you will learn out that the bosonic strings that we study, we're going to study in this course, is a Sig theory. So it has an instability. And however, everything that you will learn will be okay. And the only thing you can think that the fermions will do perturbatively is to cure this instability. Okay? So that's the attitude you have to take. All right, guys, so any questions? No, good. So we are done now. And so what we would like to do, so our string will fluctuate. And we want to know what are the spectrum of fluctuations of our string. How does it fluctuate? And so we move to study of spectrum. Well, I'll talk about open strings, and then we'll discuss generalization to closed strings. And so in doing that, we will get what I promised you before. We will find out that this capital D, the dimension in which the string can propagate. So we have to quantize this open string, and we find out that D must be equal to 26. Okay? So in other words, we obtain critical dimension of string theory. Bosonic string theory. Okay, so now, so remember that. What was our logic, right? So the natural way to think about the string and is to or the most geometrical way is to think about Nambu-Goto action. So in this Nambu-Goto action, it does not have worldsheet metric, gamma AB. And so that was actually very nice. Well, I mean, it just had, if you wish to think, it just had the fields that carried physical information. We introduced this worldsheet metric gamma AB in order to make our discussion easier. And so rather than dealing with a square root action, introducing redundancy in the description, we went to a Polakov action, which didn't contain any square roots. But the price that we pay is that now once we have a very redundant description, lots of our fluctuation has nothing to do with physics. In other words, they are just gauge transformations. The transformations due to the huge symmetry that string possesses. So what we will need to do is we need to fix symmetries of the Polakov action so that is being restricted only to physical fluctuations and figure out what is the spectrum of these physical fluctuations. So there are several ways to do it, and so we'll do it in both ways. So first we will do the fastest way possible, the fastest way that will bring us to the spectrum of excitations and will bring us to this critical dimension. And that's discussing of the string, open string theory in a light cone gauge. So we have to choose a particular gauge, right? So all I'm saying is that on the string worldsheet, there is a lot of degrees of freedom. There is a background metric, and there is a choice of worldsheet coordinates. And so what we want to do, we want to choose those objects in a very smart way, in such a way that all the redundancies will go away. We are left with physical degrees of freedom. We will quantize them, and we will get the spectrum. And the way to do this is, the fastest way is to go into a light cone. So we'll study, I'll remind you about light cone coordinates, and then we'll talk about point particle in a light cone gauge, and then we talk about Polakov string in a light cone gauge, and we then quantize it there. So I will be, since later, I will do everything very rigorous in a covariant gauge. I will be slightly sloppy, but good enough that I hope I will convince you that it makes sense what I'm going to say. So everything will be derived later in a covariant gauge. So light cone gauge. Okay, so how do we introduce light cone coordinates? Well, so remember that we are working in a Minkowski spacetime, and in this Minkowski spacetime, our background metric, eta mu nu, is -1 plus 1 plus 1. So there is this d. And then the coordinates that we have is x0, x1, xd minus 1. So those are our natural coordinates. However, what we want to do, we want to introduce a light cone coordinates. And so the way to do this, so those two light cone coordinates, I will call x plus and x minus. So I'm going to choose a time coordinate and say the first spatial coordinate and introduce x plus and x minus as follows: 1 over root 2 x0 plus or minus x1. So that's, if you wish, simply a different coordinate system, right? So once I go, and everything we're going to discuss, definitely until the end of this lecture, is in these light cone coordinates, right? In normal coordinates, well, I mean, in any coordinates, we have a contraction A mu B mu. So now I want to know how will it look like and so here that was just minus A0, B0, and then I have plus A1, B1 plus AD minus 1, BD minus 1. So now I changed my coordinates right? So now index mu has runs over light cone coordinates and then d minus 2 remaining transverse coordinates. And so in those coordinates, the dot product will look like minus a plus b minus, minus a minus b plus, and then I have plus ai bi, where I equals 2 up to d minus 1. So that's the way how the dot product will look like. And actually, now, once we change coordinates, the background metric will change as well. And so we have to provide rules, how do we raise and lower vector indices. And so the rules are as follows. So a minus with a lower minus is minus a plus, and a plus equals minus a minus. So I could have written this in a covariant way as a plus, b plus. Well, I mean, in a sort of implicitly sum indexed way, a minus, b minus, plus ai, bi. All right, guys, so that's light cone coordinates. So now I want to remind you something, or at least more like setting up my notations in quantum mechanics. So if I have coordinates on a configuration space, right? So I have my time and x. So this is quantum mechanics. So there are operators that generate translations in the spacetime. So those operators realize conjugate variables to the coordinates on a configuration space. And so the conjugate variables to t and x, conjugate variables. So the conjugate variable to time is a Hamiltonian of the system. And the conjugate variable to x is the momentum. Okay? So we can choose, if you wish, different way of thinking about quantum mechanics. And so if we choose our configuration space coordinates as arbitrary numbers and functions, then the conjugate variables become operators. And so we will have an operator representation for these conjugate variables. So this is minus I del over del x mu. So that's a momentum conjugate to the variable x mu. And so our momentum and coordinates satisfies the usual commutation relations, right? So once I give you this differential representation of operator, you can easily check that's delta mu. Okay, so that's canonical commutation relations. So the reason I'm talking about this is the following. So there is a note in Polchinski that I don't understand. So if somebody can explain me, I don't even, once you read it, hopefully it's difference between active and passive coordinates. So there is some discussion there. But I'm just giving you my way how I would make sense of what's being discussed there, and that's why I'm talking about it. So notice, and I'll point you out exactly where the issue is, what I need from all this discussion. So notice that once I have this conjugate momentum, then P naught is going to be equal minus del over del T. Okay? Because x naught is what we call time, right? So now I'm asking myself, so what is the Hamiltonian? What is the differential operator corresponding to the Hamiltonian? And well, we're all very familiar with the Schrödinger equation. So this is I del psi over del t equals to h. And so to the Hamiltonian, we have to identify a differential operator is I del over del t. So the statements that I want to make, the statements that Joe is making, and when he makes this statement, he tries to explain why that is the case. I'm just looking at this and I'm just making a statement that you can compare this. That's a differential representation for the operator P sub naught, which is conjugate operator to time, and that's the Hamiltonian. So the Hamiltonian equals minus P sub naught. He talks about active and passive variables, which you don't understand. All right, guys, so from all this discussion, and when we talk about the quantization, that's what we're gonna take. That how do we construct the Hamiltonian? We identify what is our time. We construct a conjugate variable, a conjugate momentum to time. That will give us P naught, and minus P naught is the Hamiltonian of our system. Okay, so we are done, and now we'll go back and discuss point particle in this light cone coordinate, and we'll obtain the spectrum of the point particle and discuss its quantization. Very good. So now I'm just going to reiterate what we have there. So now I'm going to choose my time. So when I talk about point particles, there is a worldline time, which we also denoted tau, and there is tau also on the world sheet of the string. So now I'm gonna, and I was free to choose that tau anywhere I want. So what I want to do now, I'm going to choose tau to be along the x plus. So it's a light cone time. And so once I do that, so there will be a conjugate momentum to x plus. So this is conjugate variable. And so now, in this light cone gauge, following the discussion there, again, I have to declare that my Hamiltonian is going to be minus P plus. Okay, minus P plus, and that's the same as a P minus. Because you remember the rules, once we can raise the index, and the index flips from plus to minus, and there is also additional signs that we pay. Okay. So in other words, so from here you can see that P minus plays the role of a light cone energy. Right? So we can talk about energies only once we choose what do we mean by time. Energy is a conjugate variable to time, and different choices of time will result in different way of thinking about energy. So that's our light cone energy. So let's look at the point particle. Let's recall the action of the point particle. So it was written in the following way. So I have del tau, eta minus 1, x dot prime, x dot minus. So the dot means derivative with respect to tau. Then I have minus eta m squared. Okay, so that was our point particle action. So now what I want to do, I want to write this action in light cone coordinate. So I have del tau. Now here I have minus 2 eta minus, and then I have x dot plus, x dot minus. So those are just plus and minuses, and there is a factor of 2 if you look at the dot product of two vectors. And then there is plus eta minus x dot I, x dot I. And finally, I have minus eta m squared. Okay? So up to now, tau is an arbitrary parameterization of the world line, but we agreed with you to align it along the light cone time. So x plus x plus we identify with tau. So what that tells us, that dot of x plus equals to 1. And so our action will take the following form: half d tau minus 2 eta minus x dot minus. Okay, so we have taken a point particle action and we rewrote it in right-hand coordinates. So now what we can do, we can compute conjugate momentum to our dynamical variables, right? So our dynamical, well, so naively, our coordinates are on a configuration space the tetrade eta, right? And then there is xi. However, yeah, okay. So let's do that. So now once we have coordinates, what we can do, we can compute canonical momenta, which is just conjugate variables to these coordinates. So that's del L over del x mu dot with respect to right-hand time. And so this equals, so for the p minus, I have to take a derivative with respect to x dot minus. So that gives me minus eta to the minus 1. So p plus is, right. So from here, I would have to conclude that p plus is going to be equals to eta minus 1. So here, all I did is just simply raise the index there. And so pi is, I have to take derivative with respect to x dot I. So there are two of these, so 1/2 will cancel. And so I have eta minus 1 x dot I. And so I can, okay, so let me keep it this way. So actually, I said here naively that eta is a coordinate, but you can see first of all that there is no eta dot, so the momentum, the conjugate momentum to eta vanishes, and in fact, you can see that eta is related to the light-cone momentum. Right, guys? So we constructed conjugate momenta to our coordinates. So our coordinates are x minus and xi. So we constructed our conjugate momenta, which was p minus and p sub I. So now what we can do, we can construct a Hamiltonian of the system, again using canonical rules. So this is just p minus x dot minus plus pi x dot I minus Lagrangian. So I'm just using the rules of classical mechanics here. Okay, and so our Lagrangian is given up here. Right? So this is our Lagrangian. This is our Lagrangian. So notice, so one note that I want to do, note that there is no term p plus x dot plus, and that's simply because when we construct canonical Hamiltonian, we have to go only through dynamical variables, and x plus is not a dynamical variable. So in principle, we could have added a piece of eta times eta dot, but the momentum conjugate to eta vanishes. Okay, so so what I want to do, I want to express the Hamiltonian as we usually do, and get rid of derivatives with respect to coordinates, and rewrite them in terms of momenta only. Okay, so if I look at that formula up here, so what I see is that x dot I is eta times pi. So this is pi divided by p plus. Okay. So I have p minus x dot minus plus pi times pi divided by p plus. And then I have my Lagrangian with the minus sign. So I have minus 1/2, right, coming from the first term. Eta minus 1 is p plus times pi over p plus squared. That's the first term. The second, sorry, no, I'm doing something wrong. Okay, that's what I'm doing. I was looking wrong. So this is the first term, and let's just look at that term. So it will come with a plus sign, so it will be plus eta minus 1 x dot minus, and then I have this other term which must come with a minus sign, so minus 1/2. Then I have p plus pi over p plus squared. And then there is a minus eta m squared, so that becomes plus 1/2 eta m squared. All right. So now eta minus 1, I have to replace eta minus 1. So eta minus 1 is minus p minus. I have minus p minus. Okay. And so this equals. So you can see that those terms cancel. So I have 1/2. I have 1/2 pi over p plus, and then I have plus 1/2 eta. So eta, somewhere I wrote what eta is. So eta is 1 over p plus. So plus 1/2 over p plus m squared. So in other words, we are finding that the Hamiltonian of our system pi plus m squared divided by 2p plus. Okay? So that's the outcome of our canonical analysis. So let me write it down again on this blackboard. H equals pi plus m squared divided by 2p plus. And so here, that's a place where we have to recall that our Hamiltonian is also is identified with p minus. So from here, we can obtain a dispersion relation, 2p plus p minus minus pi equals m squared minus 2 p plus p minus plus pi equals minus m squared, or p mu equals to minus m squared. So we obtained a dispersion relation. For relativistic part. Okay. So once we did a classical canonical analysis, we can just do canonical quantization by replacing any Poisson bracket with a commutator times minus I. And so in particular, what we will do, have to introduce these canonical commutation relations, pi xi equals minus I delta ij, and then p minus x minus equals to minus I. Then we can go ahead and quantize it, and we'll find out that a Hilbert space, the states of the particle are labeled by like on energy and momenta. Those are momentum eigenvalues. Okay. All right, guys. So I'm not going to say anything more on the point particle, but I'm going to now move to the strings, and we'll do all the same, slightly more in some more detail. And do first classical canonical analysis, and after that, we will go ahead and quantize the string, solve the equation of motion, and find the spectrum. So let's, so I'll keep talking until 11:50, and then we'll have a 10-minute break. Are you all right? Is that okay? Okay, let's go ahead. All right, very good. So, so what we're going to do the same for the string, Polchinski string. All right, so we're going to consider open string. Right, so tau goes from minus infinity to plus infinity, and variable sigma from 0 to L. So the Polchinski action has some redundancies. So, so exactly how many redundancies are there in Polchinski action? Well, so first of all, tau, I can go to any other coordinate by simply changing tau and sigma. So tau goes to tau prime, sigma goes to tau and sigma. So that's two arbitrary functions. Two arbitrary functions. So our action is diffeomorphism invariant, so I'm free to choose those guys as much as I want. And actually, by choosing those two functions, I, at least naively, again, we'll return back to why I'm saying naively here much later, but for now, it's rigorous, okay? By choosing my coordinate system, I completely fix the diffeomorphism invariance. And there is a third freedom that I have. So remember, our action was invariant under wild transformations, and that wild transformation came with an arbitrary function, tau plus sigma, so plus one more. So altogether, we have three conditions. We need to impose three conditions to fix diffeo plus wild symmetry, right? So our action, our quantum field theory has these redundancies. And so once we want to talk about physical excitations in that field theory, we better get rid of this. Okay, so so there are various ways how you can fix those three invariances. So we need three conditions. If you ask me, would I be able, how would I guess that that's the right way? Well, I wouldn't know. So I honestly don't know what we're going to do here is that somebody told us that's the right way to proceed, and we'll take it and see that indeed it simplifies things dramatically. Okay. Now, I guess what I'm trying to tell here is that it's difficult for me to motivate why that particular choice I'm going to make without, without making the choice, doing the computation, and showing that the action becomes simple. So, so let me say how bad it is. So I told you that we need to fix we need to provide 3 conditions. So the first condition is that we're going to choose the light cone gauge, right? So the second condition, we're going to impose this particular property on a sigma-sigma component of the metric, del sigma gamma sigma sigma equals to 0. And the last one, so we're going to impose a condition, the determinant of gamma equals to -1. Okay, so those are our gauge fixing condition. So why, you ask me, I did this? I don't know. What I'm going to show you that once we choose gauge condition in this way, then we will get a very simple quadratic action, which will look very similar to the action of a bunch of relativistic particles. Okay. Now, what you should be asking me is that, is this gauge choice consistent? So there are 3 conditions, but those 3 conditions look completely different from the conditions that I would be doing if I were to try to fix diffeomorphism invariance and the wild invariance. And so what we need to do, we need to show that we can always choose this light cone gauge. So this is what's known as a light cone gauge. Light cone gauge for Polyakov string. And so what we need to show that it's always possible by choosing a wild transformation and diffeomorphism reparametrization on the wall sheet to achieve those 2 conditions. This is obviously true. I can always do that. So we can always choose light cone fixing locally. Okay, so let's go and talk about that. So again, the purpose here is to show that I have enough freedom in diffeomorphism invariance and wild transformation to impose those conditions. Okay, so well, the first thing is obvious. We're going to set x plus equals to tau. That doesn't require anything. But the next thing, we're going to consider the following function. So we're going to consider why is that? So we're going to consider the following function that I'm going to define as gamma sigma sigma, and then I have minus gamma to the -1/2. Okay? So the first thing I want to show is that so what we're going to do, we're going to keep tau fixed. So everything that I'm going to discuss, I'm going to keep my wall sheet time tau fixed. And then I'm going to show that f times d sigma is the same as f times d sigma prime. So if I change my sigma coordinate, then this quantity represents an invariant length element. Okay, so this is my invariant length. Right? So it's invariant under residual reparametrization of spatial coordinate on a whole sheet. Okay? So let's see that that's indeed the case. Well, so what we need to do, we need to compute f prime. So f prime is gamma sigma sigma prime minus gamma prime to the minus 1/2, and it's equal. Well, so suppose I make change of variables, and so meaning that I keep tau fixed. So sigma goes to sigma prime, which is a function of sigma. And so as I make this change of variables, so sigma sigma will go to sigma prime, which is going to be equal gamma sigma sigma. And then I have d sigma over d sigma prime squared, right? So this is just the way how the metric will transform. And then I need to care about the other component. So sigma tau will go to sigma tau prime, which is going to be sigma tau d sigma over d sigma prime. So instead of two derivatives, there will be one derivative here on this lag. And finally, sigma tau tau will go, sorry, gamma tau tau will go to gamma tau tau prime, which will not transform. And the reason for that is that we are not mixing tau and sigma in this transformation. So if you do that, so you can see that this becomes sigma sigma d sigma over d sigma prime squared, okay? And now I have a metric, so let's see how the determinant of this gamma prime will transform. Well, I have to compute a determinant, which is this guy times this guy minus the square of this guy. So you can see that what I will be left with d sigma over d sigma prime. So I will have minus gamma, and so this is d sigma over d sigma prime squared. And so the metric, the determinant of the metric is raised to the minus 1/2. And so this guy is going to be raised to the minus 1/2 as well. Okay? So now you can see that this f prime, so here that will flip the order, and 2 will become 1. So 1 power here will cancel. So I have my old function f times a single derivative d sigma over d sigma prime. Right? So we showed that f prime equals f times d sigma over d sigma prime, which is exactly what I wanted to show. So from that, it immediately follows that f times d sigma equals f prime d sigma prime. Okay? So this is a very important property because it tells us that f d sigma is an invariant length element. And so that tells us that, well, dl over L, well, actually, I apologize that I'm going to use the letters that I never will use before or after, which is this capital letter L. So this capital letter L, sigma equals 0, and sigma equals capital L. I don't want it to confuse if I write little l there in the denominator. That's not a variable. So I'm writing down an invariant length, dl over capital L. So it's going to be equal. To, so if I integrate this over the sigma interval, I will get 1, right? And so here on the right-hand side, I'm going to write down the quantity which I integrate. I will get 1 as well, which is f d sigma divided by integral from 0 to L f d sigma. Okay? So so at this stage, it's just an identity. But now I'm going to, up to now, my sigma coordinate was anything. So now I'm going to choose. So what we're going to do, we're going to choose d sigma to be equivalent to this dl in the invariant length along the wall sheet. So once we did this, so now now I have the dl over little l equals f dl over integral from 0 to L F d sigma, right? So what I did, this is the choice that I made. So I made now two diffeomorphism choices. So the first one was when I said this one. So that was my first diffeomorphism choice. So my second diffeomorphism choice is here. So I choose completely diffeomorphism reparameterizations on the wall sheet. Now, if you look at this identity, what this tells you that my function f takes the form 1 over L times an integral. I don't want to make an algebraic mistake. F d sigma. Okay? The important thing, which is an obvious statement now, is that this guy, in this gauge, for this choice of sigma, del sigma of f equals to 0. It vanishes. It's an obvious statement because I told you what in my coordinate f is, and it's given by an integral of a sigma. There is no sigma dependence anywhere, and there is just a factor of 1 over L. So in this particular, after we fix diffeomorphism choices, my f is independent of sigma. So, so it's del sigma f equals to 0. So now, what we are left with Weyl symmetry. And so remember that Weyl transformation gamma AB goes to gamma AB times e to the 2 omega. So, so the metric gamma will go to gamma times e to the 4 omega. So, so the point is that I can always use, we can choose choose omega so that gamma prime, which is going to be gamma e to the or omega equals to -1. So that's an obvious statement. You tell me what the metric you have, and I can rescale it. I can introduce a Weyl factor in such a way that the determinant of the new metric will be equal to -1. So the important thing, now you have to worry. So here I fixed diffeomorphism invariance. Here I fixed Weyl reparameterization in this particular manner. But now I'm going to show you that everything that we did so far is invariant under Weyl transformation, meaning that there is no contradiction with imposing those two conditions. And so what we're going to show, that f is Weyl invariant. So once we show that Weyl invariant, this means that we can simultaneously impose a condition that determinant of gamma equals to 1, and plus insist on that condition that del sigma of f equals to 0. So that thing is actually very simple. Right, so, okay, so I don't have it. I shouldn't be making a mistake. So remember that f is gamma sigma sigma, and then minus gamma to the -1/2. So f goes to f prime, which is gamma sigma sigma e to the 2 omega, right? So there is e to the 2 omega from Weyl transformation of this factor. And then there is minus gamma to the -1/2. And then there is e to the 4 omega to the -1/2. And so you can see here, indeed, that my f is invariant with respect to Weyl transformations. So the bottom line is fixing diffeo plus Weyl in a way how we discussed. I can impose two conditions, that del sigma of f equals to 0. I can achieve two conditions, and minus gamma to the -1/2 equals to 1. The determinant of the metric on the wall sheet equals to 1. However, notice that this immediately implies del sigma gamma sigma sigma -1 to the -1/2. This is the same as del sigma times gamma sigma sigma, right? Because determinant equals to 1, I can just substitute that it's equal to 1 in this coordinate. And so I am achieving my gauge fixing condition that 0 equals del sigma gamma sigma sigma. In other words, gamma sigma sigma is a function only of tau. Okay, so everything that we discussed so far, we didn't keep track of tau. We fixed our light cone tau. And so whatever answers we are getting, whatever conditions we are getting, they can depend on tau. And so that's reflected in this condition. All right, guys, so we showed that there is a well-defined light cone gauge. We can always choose it, at least locally. So what we're going to do after 10 minutes, we're going to show that canonical description of Polyakov string is very simple with these choices.